We're wrapping up the first part of the course. Now, the first part of the course is the techniques of integration. And, of course, we've learned a lot. And so it's a good time to pause and check what we've learned, which means a test. So we have a test coming up. So we're going to do a little bit of review today. And review here means we're going to practice problems, because the best way to get good at solving problems is to solve problems. And I want to give a little piece of advice. Now, here is an approach to solving problems, and this comes from a book by a very good mathematician. His name was George Polya. He said, look, there's really 4 parts if you want to solve a problem. Part 1, you've got to understand the problem. That's pretty good. And in particular, you have to say, what do we know? What are we given? And what are we looking for? And how are these connected? So in the past, I've seen students who are just so excited to start solving a problem that they read the first few words and I said, I know what's going on, and they jumped in. But if they'd read a few more words, they would have said, oh, that's not what's going on. Oh, this is really what's going on. So don't rush to answer a question until you know what the question is. So take some time and make sure you understand it. Now, once you understand the problem, develop a plan. Have you seen a similar problem? And the answer is, yes, you have. Because we've given you lots and lots of problems. And in particular, we're not testing you using tools you haven't learned. We're testing you on tools you have learned. Now, one of the big things to figure out is what tools apply and which don't. And that's the hard part. That's one of the hardest things to do, is to say, okay, here's a problem. What tool do I use? Because there are many tools. And indeed, previously, you had a tool, substitution. Now you have about 5 or 6 tools, and that can make it a little bit more challenging. So you should think, what tool apply? What tool applies? And then, of course, can you solve part of the problem? Can you restate the problem? Oftentimes here, restating, you can almost think of that as like a substitution. Maybe I can use a substitution to rewrite it. Then, okay, we understood, we've developed, carry out the plan. And here, check each step. And notice, it's not just check each step, it's check each step. You gotta really check, because small mistakes will cascade into bigger mistakes. You don't want that. You don't want it. Can you see your answer is correct? You look and you say, this is reasonable. I once had a problem about finding the height of a mountain on a test. This was many, many years ago. And students would turn in answers saying, well, the mountain is 15,000 miles tall. That's a really tall mountain. That's impossible. There's no mountain on earth that's 15,000 miles tall. Okay, there was mistakes made. But they didn't stop to say, I wonder if this could possibly be correct. So think about it. Think about it. Can you check the result? All right. Is it reasonable? Well, can you do a similar problem? Now this really, when you ask, can you do a similar problem, it says, look, maybe someday in the future, you'll have to do something again. Well, that's likely. And so what you want to do is you want to say, well, let me practice doing problems now so that someday I can do problems then. So that's why we keep doing problems. We do problems because someday we'll be asked to do other problems. And that's why it's important. Every time you do a problem, okay, what did I do? Why did I do it? And can I do it again? So that's advice on solving problems. Here's some general advice about the test. And this is really any test. So some of these should be hopefully obvious. For example, number 1 says, be well rested, physically ready. Well, we've had students fall asleep during tests. It's a very poor strategy. They didn't do very well. So look, get your sleep. Get your body physically there. You might think, wait, this is a test. You're testing my mind. But if your body is not physically ready, your mind will definitely not be as well. And another thing, I strongly discourage drinking a big gulp before the test starts. Because there's something about nerves that shrinks the size of your bladder. So you don't want to overhydrate yourself. If you feel like you might need to, get an aisle seat so you can quickly dash to the restroom. Now, number 2, look, understand ideas, not just procedures. So if you say, look, I know all the algorithms step by step. Well, look, do you understand what's the idea behind them? Because oftentimes we might say, well, here's something slightly different than what we've said before. But it's the same idea. Can you adapt to this new situation? Number 3, be calm. It's natural to be nervous. I'm not saying don't ever be nervous, because there is some pressure. The test is a significant part of your grade. However, don't go into panic mode. When you start panicking, you start doing crazy things, like, for example, thinking that the square root of a squared plus b squared is a plus b, which is never true. Which is never true. You should be relaxed. We've given you all the tools that you need to succeed. So breathe in, breathe out. You'll be fine. You have all the tools that you need. Now, when you're doing a test, work on the ones you know first before getting stuck. Well, because get all the points that you can. Look, we're calculus people. We like to optimize. We like to get the most. And so, in this case, get the most points. So don't say, I'm going to do the problems in order, no matter what. And you go to problem 2 and you're like, wow, problem 2, I don't know what to do. So I'm going to spend the next 75 minutes staring at problem 2 and don't make any more progress. Well, in the meantime, problems 3, 4, and 5 you could have done. And now you lost those points. And there's an interesting phenomenon, which is you start a test and you get stuck on a problem, like, I don't know what to do. I'll come back and look at it maybe later. And you go and you work on other problems, and by the time you get back, you're like, you know what? I have an idea. Something has happened in the meantime. Your mind has kept churning, coming up, saying, what about this? What about that? But it's all been done in the background. And just by the time you get back, it says, here's our best thought about what to do. So it's okay. Make sure you know the problem before you move on, but it's okay to come back and do things later on. Check your work. And remember, no calculators are allowed. And so, if your problem starts getting worse and worse and worse, something's happened. Something not right has happened. So slow down and say, I wonder, perhaps I should stop and check my work. And finally, this is not advice about the test, but it's important to say, we do not look at your worth as a human being as dependent on your test score. People who get 60 out of 60 are not people who we love, and people who get below that are not people that we don't love. No. We love all of our students. We work really hard. We want everyone to succeed. That's our goal. We want all of you to succeed. But even if you don't get a good score, we're still going to try to help you succeed, because that's our job. But it's more than our job. This is what we love to do. And we really want you to do well. So, some advice. All right. Good luck on the test. It's going to be interesting. And keep coming back after, because we still have 2 more parts of the class to go. Now, we said this test is about integration techniques. Well, what are integration techniques? We've learned 6. So the 6 basic things that you need to know are integration by parts, which, remember, is basically, it's the product rule, just expressed in terms of integration. Doing integrals with trigonometry, doing trig substitution. Trig substitution is when you have square roots of a sum of squares or square roots of a difference of squares. And you use the trigonometry to help you get rid of the square root. Partial fractions. Partial fractions are rational functions. If you have a polynomial over polynomial, that's a partial fraction. And you automatically, there you go. Numerical integration. Now you have a problem that says, look, this integral, for whatever reason, we can't do. Maybe the function's too hard to integrate, or maybe we just don't have information about the function at all points. Maybe we've sampled some data. We're saying, okay, well, perhaps I can get enough information from the sample to say what the answer should be, approximately. So numerical integration is basically approximation. How can I approximate the answer? And the one we just talked about, improper integrals, which is basically integrals which involve infinity. So you break those up and you say, look, take each problem with infinity and make it its own little thing and work on each one and then put them back together. So the way you deal with improper integrals is as limits of proper integrals. All right, and proper integrals are, for lack of a better word, proper. So you can do those. You can do those. And this, of course, gives us a chance to use one of our favorite results, l'hôpital. Oh, l'hôpital. Very popular result. One of the most popular results that we have from Calculus 1. All right. Now, one of the things that does happen is that people start to say, oh, I've learned 6 ideas. I have 6 little boxes. And so whenever I see an integral, I'm always going to put it into one of these 6 boxes and use only that technique. But the thing is that these lines here should really be blurred. It's very possible to start a problem with one technique and then halfway through switch to a different technique. It's possible. In fact, it happens. So don't get too caught up on saying, oh, I have to use such and such. No, you don't have to use such and such. It's just see where the problem takes you. See how the problem develops. And that will tell you what to do. That'll help you figure it out. And of course, again, learn to recognize when to use what techniques. If you can help figure out, aha, this is where I need to use a certain technique, then you're 80% there. Okay. So for the rest of the time, we just want to go through and do some problems, because that's how you get better. You do problems. So we're going to do a whole bunch of these, and hopefully by the end, we're going to be pretty good. So our first problem, all right, you can tell, one of my favorites, because it has an arctangent in it. Find the integral of arctangent of x over x cubed dx. So, okay, let's think about what technique we could use. We can rule things out. It's not a polynomial over a polynomial, so it's definitely not partial fractions. Let's see. There's no trig substitution, because there's no square root of a sum of squares or a difference of squares. It's not an improper integral, because improper integrals have to be definite integrals from some point to some point. This is an indefinite integral. So we're really running out of things we can do. There's no trigonometry. I mean, arctangent is a kind of a trigonometric function, but we talk about trig integrals. That's sines, cosines, secants, tangents. There's no numerical integration, because again, numerical integration is about approximating a definite integral. So this one, by process of elimination, we really are saying it needs to be an integration by parts. But even if we didn't get to this by process of elimination, we could say, you know, arctangent, that's something we can have, that's a good derivative. You know, the derivative of arctangent is 1 over 1 plus x squared. But of course, the integration is messy. So if you ever have a problem where one part is a really hard thing to integrate but has a lovely derivative, you say, aha, that should be integration by parts. So I'm going to think of this as arctangent of x. This is my one part, and that's going to be the part I take the derivative of. So I'll call that u. Then I have 1 over x cubed dx, and that I'll call my dv. So derivative of arctangent, well, that's 1 over 1 plus x squared, because arctangent is awesome. All right. Integral of 1 over x cubed. Well, you can think of 1 over x cubed as also being x to the minus 3. And now, if you write it in this way, you say, aha, add 1, x to minus 2, and then divide by that new exponent. Or if you like, minus 1 over 2x squared dx. Well, good. Except, whoops, I don't need a dx. All right, fix my notation. I just cross off what I don't need. I don't have to go back and rewrite it. All right. Now, integration by parts says you can have u, v. So minus 1 times arctangent, so I'll write this as minus arctangent x divided by 2x squared. Good. Then minus the integral of v du. Now there's already a minus there, so minus minus makes plus. The integral of 1 over 2x squared times 1 plus x squared dx. Now, we just did integration by parts. So we have our integration by parts hat on. But we've gone to a new point. We've gone to a point where there's another integral. That doesn't mean we have to keep our integration by parts hat on. Let's take a look and see what we have. And if we look, we say, whoa, wait a second. That is a polynomial 1 over a polynomial. Well, we've gone from integration by parts, and now we've jumped over to partial fractions. So this is why I say you can move around. The problems, they can tend to blend together. So I'm going to switch gears and say, look, this is now a partial fraction. And indeed, if this was a partial fraction, I'm going to think of this as 1 over 2x squared times 1 plus x squared. I'm going to break it up as something over x plus something over x squared plus cx plus d over 1 plus x squared. So that is a lot of partial fraction going on. But that's okay. We have time. So that says 1 is equal to a times x times 1 plus x squared plus, oh, I forgot my 2, 2a plus 2b 1 plus x squared plus, and I really misjudged this, 2x squared times cx plus d. Okay. So what happens next? Well, what happens next is we start solving. Now, in this particular problem, you'll see that there's one good choice for x right away. If you choose x equals 0, then what will you end up with? Well, 1 equals 0 plus 2b plus 0. So 1 equals 2b, which tells us that b equals 1/2. Unfortunately, that's more or less the last good choice for x. So what do? Well, here we can go ahead and do various other things. So for instance, we can do our gather coefficients. So what happens? Well, we would have 1 is equal to 2ax plus 2ax cubed, and then plus 2b plus 2bx squared, and then plus 2cx cubed plus 2dx squared. And now, well, what do we have? As they say. Well, we should say we know what 2b is, so 2b is 1. So I'll go ahead and replace this with 1 and 1. And notice I have a 1 and a 1. They actually end up canceling each other. And so I get that 0 is equal to, now let's gather the coefficients. We'll start with highest power. So there's an x cubed and an x cubed. So 2a plus 2c times x cubed. Then plus, where's my x squareds? Well, there's an x squared and an x squared. So I have 2b plus 2d times x squared. All right, so let's just check what we've gathered so far. And then plus 2a times x. Okay, good. And I should have said 2b is 1. Now, notice there's no x. So that tells us that 2a, that better be equal to 0, which says that this part is equal to 0. But again, there's no x cubed. This means this part is equal to 0, so we can conclude that this equals 0. So now we have that a and c are both 0. And finally, there's no x squared. That means that this better be equal to 0. 2d better be equal to negative 1, or d equals negative 1/2. So in fact, 2 of our terms are gone automatically, which leaves us with just 2 terms left. So a is gone, and also c is gone. So what do we have? Well, at this point we have the following. So we still have our minus arctangent of x over 2x squared plus integral. And now we have 0 over x, then 1/2 over x squared. So I'll write this as 1/2 times 1 over x squared. And then we're going to have plus d, because the c is 0. D is minus 1/2, or minus 1/2 times 1 over 1 plus x squared. Okay, dx. And now we're almost done. All right. So minus arctangent x over 2x squared. Integral of x squared downstairs, well, x to the minus 2. That becomes x minus 1 when you integrate, and then you get a sign. So minus 1 over 2x. All right? Then 1 over 1 plus x squared. Come on, we know that one. That's arctangent x over 2. And because this is an indefinite integral, we add the c because we want all the points. Done. Done. Okay. So really, not too bad. It was, let's do integration by parts once. Let's do partial fractions. See where the problem takes us. See where the problem takes us. Okay, let's do another one. Of course, different kind of problem. So we have lots of different problems. Here we go. Let's use the trapezoid rule with n equals 4 trapezoids to approximate the integral sine pi x from 0 to 1. Now, it is a definite integral, so it makes sense to talk about using a trapezoid rule. Because you can only do trapezoid rule for definite integrals. Well, what do we do? All right. What we can do is think about what's happening here. So n equals 4 says I'm coming here from 0 to 1, and I want to split it up into 4 pieces. Well, that's not too bad, because you can split it into fourths. So 1/2, 1/4, 3/4. And notice the widths are all the same. So all the widths are equal to 1/4 of the length, so 1/4, because I'm going from 0 to 1. Now, what do I need to know? Well, I need to know what happens at these points. Because essentially what's happening is I'm sampling. So at 0, what happens is I get sine of 0, which is 0. At 1/4, I get sine of pi fourths, and sine of pi fourths is, that's right, 1/2 square root of 2. Good. And then at 1/2, sine of pi halves is 1. And at 3/4, I get sine of 3 pi fourths, which is, again, 1/2 square root of 2. Good. Good. And at 1, sine of pi, 0. Okay, so now I know what the values are at the points. I've sampled. I've seen what's happening. Because I only need to know where I'm at these particular points. All right, so here we go. What does the rule say? Well, if we go back to the trapezoid rule, as presented in the book, it's 1 over 2. Now 2 comes because we're going to be averaging endpoints, times the number of intervals, 4. And then what we do is we're going to look, all right, in this way first, f0 plus 2 f1/4 plus 2 f1/2 plus 2 f3/4 plus f of 1. Now that's the general rule. Now let's actually put in our values. So that's 1/8. Then I'm going to get 0 plus square root of 2 plus 2 plus square root of 2 plus 0. Because I've multiplied 1, 2 of these, 2 of these, 2 of these, 1 of those. Okay. So what's our answer? Well, there's 2 square root of 2. That's 2 root 2 and a 2. There's an 8. So that would give us 1 plus square root of 2 over 4. All right. Okay, well, that's good. Let's have that kind of problem. And really, numerical integration is not so bad. It's just a matter of follow the formulas. What does the formula tell you to do? What does the formula tell you to do? Okay. Good. How you doing? Good. All right. Well, let's do another one. Okay. Well, here's another definite integral. Integral 0 to 1 dt over t times log t squared minus 3 log t plus 2. Well, this is a strange integral. Now, you might notice 0, you're going to have a problem because downstairs you're going to get something really weird. You're going to get 0 downstairs. We also get log of 0, which is like negative infinity. So there's some crazy stuff happening downstairs, and it's not totally clear what's happening, but we'll sort of deal with that when we have to deal with that. But there's certainly, we should think, something's not right at 0. And if you were to graph this, of course we don't have graphing calculators allowed, but if you were, you would say something's definitely not right at 0. All right. But beyond having problems at 0, this is a really messy looking integral. And it's not so clear we can do this one. So how can we rewrite it? What can we do? Well, we go back to our big tool. So our big tool for working with integrals that look messy is to say, well, don't do those integrals. Rewrite it. And the way we rewrite things is by substitution. And the question is there a nice substitution? So, is there a nice substitution to make here? The answer is log. Because first off, we see logs here, and we see this 1 over t. Well, that's the derivative of log. So again, if you think about it, this 1 over t dt, that's set up to be the derivative of log t. So here's our thought. Let's make u be log t, and this becomes our du. So this would become integral, again, dt over t is du over u squared minus 3u plus 2. Now let's talk about our bounds. So again, if we think about u as log t, well, if I plug in 1, log of 1 is 0. That's not bad. Plug in 0. Well, I can't plug in 0. Log of 0 is undefined, but I can think about what's happening as I go to 0. So what happens to log as I go to 0? Log goes to minus infinity. Okay. So now we've basically traded one improper integral for another improper integral. However, where this one looks like, this one's like, yeah, that's right. It looks nicer, cleaner. And really we say, okay, look, this looks like a very nice integral to work with. Indeed, we can say partial fractions, polynomial over polynomial. Okay, so idea with partial fractions is let's factor. So here we go. What does that become? Well, u squared minus 3u plus 2, that's u minus 2 times u minus 1. And again, you will be left with the false belief that everything factors by the end of this class, because we're going to make sure we give you things you can work with. That's our goal. Give you things you can work with. Well, okay, let's see if we can squeeze a little bit of partial fractions here on the side. We'll change colors just to make sure we differentiate what's happening. So, that's probably not going to show up very well. Let's go with more of a purple color. So, if I have 1 over u minus 2 times u minus 1, I want that to be something of the form a over u minus 2 plus something b over u minus 1. Clear the denominators. 1 should be equal to a times u minus 1 plus b times u minus 2. And now, this is really the kind of partial fractions we like. We say, hey, let's just choose nice values for u. If I choose u equals 2, what do I get? Well, 1 equals a. Well, another way to write that is a equals 1. Oh, yeah, of course that's another way to write it. Other thing, u equals 1. 1 equals, that term goes away, minus b, so b equals minus 1. Okay, so we now squeeze in a little bit of partial fractions on the side. Good. Back to our regularly scheduled problem. So negative infinity to 0. And again, what I'm doing here is I'm just rewriting the integral on the inside. So I can do that. That has nothing to do with whether it's improper or not. I'm just saying, here's a different way to think about the function. You're absolutely allowed to do that. 1 over u minus 2 minus 1 over u minus 1. Now we say, well, look, really to do this right, it's improper. So let's now say, what does this become? So limit b heads to infinity, negative infinity, integral b to 0, 1 over u minus 2 minus 1 over u minus 1. All right, well, now we have an integral we can do. That's always what we want. All right, so that's log u minus 2 minus log of u minus 1, evaluated from b to 0. Now notice I have a log minus a log. Well, log minus a log lets me say this is really the same as log of the difference, u minus 2 over u minus 1. And also, might be a little bit nervous. We can always put absolute values in here, just if we're nervous about the fact that we're dealing with negative numbers. Okay, now the question is, what happens when I evaluate from b to 0? Well, this is going to become limit b goes to negative infinity. And if I plug in 0, 0 minus 2 is negative 2. 0 minus 1 is negative 1. Negative 2 over negative 1 tells me I get log 2 minus log b minus 2, b minus 1. Finally, what's happening as b goes to negative infinity? Well, log 2, it does nothing. It's always log 2. But here, b minus 2 over b minus 1. Well, b minus 2 over b minus 1 is getting closer and closer to 1. So this inside gets close to 1. Then I have log of that, log 1. Well, okay, so log 1 is 0. And so in the limit, the last term drops out, and therefore the answer is log 2. Now, I should have done one more thing before I got too far along in the process and said, are there any other problems? Because maybe there was some sort of vertical asymptote in the middle. But here when we write it in the u minus 2 times u minus 1, we can see that the asymptotes would have occurred at 1 and 2, which are definitely not between negative infinity and 0. So we were okay. So that's it, log 2. So that messy looking integral turns out has a nice answer. Well, that's nice. All right. So now let's try something else. Okay. Here we go. Integral cosine to the 5th theta over sine to the 3rd theta d theta. So now we have something where we have trigonometric functions. Well, what technique should we use? Probably the one about how do you integrate trigonometric functions, trig integrals. All right. Good plan. Well, so how does that work? Well, what do we do? The answer, well, for cosines and sines, what's our best situation? It's to have one of the exponents be odd. Now in this case, we actually have both the exponents are odd. You might say, wait a second, but sine cubed is downstairs. It is downstairs, but it's also odd. So which one do we use? Well, the answer is the one which is going to create the least amount of work, and that is the one that's upstairs. If you try to do too much downstairs, you're going to create heartache and suffering. We don't want that. We want our problems to be smooth and gentle. And so we say, okay, let's pull off the odd one upstairs. So if I do that, I'm going to have cosine to the 4th theta over sine cubed theta, and then a single cosine. So I'm pulling off one of my odd terms, because what's going to happen is I'm setting myself up for a substitution. And the substitution is going to end up being whatever gives me the derivative is as cosine. Well, that tells me I should make my substitution be sine. So I need to make sure everything is going to be in terms of sine. Now cosine to the 4th, well, that's cosine squared squared. So cosine squared squared over sine cubed. And of course, cosine squared squared is 1 minus sine squared squared over sine cubed times cosine. And now we're in good shape. Make the substitution. So what's our substitution we're making? We're going to say u equals sine, then du is cosine. So if we have that, then what do we get? Well, we get that this is equal to the integral of 1 minus u squared squared over u cubed times du. Okay, now we've transformed a trigonometric integral into a polynomial. And we're like, oh, this is partial fractions. But hold on, do we really need partial fractions? Because we don't need to really break up the denominator. It's all u cubed. Well, so that means, what should we do? Well, let's factor upstairs. So 1 minus 2u squared plus u to the fourth over u cubed, which is 1 over u cubed, then minus 2 over u plus u. And now we're almost done. I did not plan well, so let's see if I can squeeze it in. So the integral of 1 over u cubed, we actually did this earlier, so that's minus 1 over 2u squared. Then minus 2 over u is going to be minus 2 log u. Then plus u is 1/2 u squared. And to finish it up, because this is an indefinite integral, so we remember the plus c, put everything back in terms of our substitution, which was sine. So minus 1 over 2 sine squared minus 2 log sine plus 1/2 sine squared plus c. And then we're done. That's the answer. Now, you could say, well, shouldn't I replace sine squared by cosecant squared? And you can, but you don't have to. We're not testing you on can you rewrite using trigonometric functions. So that's perfectly fine. Perfectly fine. All right. Now you might wonder, could I have pulled off a sine? And the answer is yes. You'd multiply both top and bottom by sine. And then you could say, well, sine to the fourth downstairs becomes 1 minus cosine squared squared. And oh my gosh, that leads to partial fractions and messiness. And we don't want that. We want nice, simple problems. We want to have fun. That's our goal. Let's have fun. Let's have fun. Okay, next one. So find the integral 1 over y cubed times the square root y squared minus 1. How do we do this one? How do we do it? Well, first off, what technique should we be thinking of? So I have here a square root of y squared minus 1. So that's really y squared minus 1 squared. So when I see a square root with a difference of squares or a sum of squares, I think trig substitution. Okay, so let's do that. Let's do a trig substitution. Well, what's the right trig substitution to make? If I have variable squared minus constant squared, the answer is I should choose y to be secant. Okay, so if I choose y to be secant, that says dy, well, that better be secant times tangent, d theta. And on a side note, square root of y squared minus 1 has been set up. Well, that becomes the square root of secant squared minus 1. That's the square root of tangent squared, so that's tangent. All right, so if we make this substitution, we now have 1 over y cubed, secant cubed, then times square root of y squared minus 1 times tangent, then times dy is times secant times tangent. Okay, well, we start canceling, and we get down to 1 over secant squared. Well, 1 over secant squared is what? It's cosine squared. Now, I don't know how to integrate cosine squared. It's messy. So the way I integrate cosine squared is to not integrate cosine squared, but to use a trig identity. because there's always a trig identity, and it's one of the ones we should know. So cosine squared is the same as 1/2 plus 1/2 cosine 2 theta. So we can integrate. That's 1/2 theta plus, all right, integral of cosine. Integral of cosine is sine. Same, and we keep the same plus. But I have to accommodate for that 2 on the inside. So that makes this a 1/4 sine 2 theta plus c. Now I want to get back to where I started. And to help me get back to where I started, I need to get back in terms of things like sine thetas and cosine thetas and secant thetas and tangent thetas. And the problem is I have a 2 theta. So now we pull out another trig identity which says, hey, sine of 2 theta, I know that one. So sine of 2 theta, that is 2 times sine theta times cosine theta. So that is going to become 1/2 sine theta cosine theta. And now I have everything in terms of thetas and sine thetas and cosine thetas. That's a good situation for me to be in. So if I come back up here and I draw my chart really quickly, I'm going to draw a little triangle. So here I'm going to put theta in the corner. Secant is hypotenuse over adjacent, and that's supposed to give me y. So I can write this as y over 1, which means that my missing side is square root of y squared minus 1. No coincidence, I have a square root of y squared minus 1 there to begin with. And so, what do I have? Well, this will be 1/2 theta. Well, theta is arcsecant of y plus 1/2, well, sine theta. Sine is opposite over hypotenuse. Square root y squared minus 1 over y. Cosine theta, adjacent over hypotenuse, 1 over y, and then plus c. So if I wanted to, I could rewrite this 1/2 arcsecant of y plus square root y squared minus 1 over 2y squared plus c. And we're done. Done. Good. Good. So this is a fun problem. It's sort of like, okay, make the substitution, and then you get to a certain point where you have to do a trig integral, but it's a trig integral using techniques that we're used to. In this case, the technique here is to say, oh, power reduction. And then we get to use more techniques. We get to use double angle identity. So this is fun. This is fun. All right, well, that was only 5 problems. We've actually tested on all the ideas. So let's just, for fun, do one more for a cool down. In fact, this one will have 2 parts, a part A and a part B. Okay, so part A, find the integral from 0 to 1 of square root of 1 minus t squared. Well, we've actually done this before. Because if you think of what square root of 1 minus t squared looks like, from 0 to 1, it's a quarter of a circle. So I can use geometry and say, well, it's 1/4 of a circle of radius 1. So, since I know the area of a circle, I can conclude that this integral is 1/4 pi. Okay, so part A, that was pretty straightforward. Use geometry. Part B, well, we only make a small change. How much can that really affect us? Integral from 0 to 1, square root of 1 plus t squared dt. Well, now the problem is it's not a circle. It's a part of a hyperbola. And so, unfortunately for us, we don't learn the volume under hyperbolas because, for one thing, it's not a contained space. If it's not a contained space, there's not a nice formula because, in some sense you could argue there's infinite. All right, well, don't use geometry. Then we'll just go back and say, look, I got the tools. I've got calculus. I'm unstoppable now. You can't pull me down because I'm gonna get back up again. So here's what we're going to do. We're going to say, what do we do? I see a square root, sum of squares. That tells me trig substitution, and in particular, it says, look, how about I put in a tangent theta? All right, that's perfectly allowed. Then what will happen? Well, dt will become secant squared, derivative of tangent, secant squared. It's on our list of things to know. Square root of 1 plus t squared, well, that becomes square root of 1 plus tangent squared which becomes square root of secant squared, which becomes secant. All right, we can live with that. And now we update. So here we go. Integral 0 to 1 square root 1 plus t squared dt is equal to integral, and then I'm going to have a secant times a secant squared, which gives me a secant cubed d theta, and we can even update our bounds. So remember, these bounds over on the left, these are t bounds. T equals 0, t equals 1. I want to go to theta bounds. Theta equals 0. Whoops. Or to theta equals something. I don't know what it is. To theta equals something else. So if t equals 0, what angle, tangent to what angle gives me 0? And I did a little Freudian slip. It's 0. Now, if t equals 1, tangent of what angle gives me 1? The answer is pi fourths. So tangent of pi fourths gives me 1. All right, well, there we go. So I'm going from 0 to pi fourths, secant cubed d theta. Well, hey, trig integrals. Good. So we did a trig substitution, and now we got down to a trig integral. All right, and this is one of those trig integrals that involves secants and tangents. And there's one of three possibilities. Well, one thing is, maybe I can pull off a secant squared and have everything left in terms of tangent. Well, the problem is, if I pull off a secant squared, there's a secant left. I really can't get that in terms of tangent in a nice way. Okay, so we won't do that. There's another possibility. Maybe I can pull off a secant tangent, have everything left in terms of secant. Well, there's not really a tangent. Then there's the last possibility. Secant to an odd power. Oh, that's what we have. And I remember that in the last possibility, secant to an odd power is, work. How do we get that? Well, let's see if we can remember. So that one, if we were doing secant to an odd power, and in particular, let's just do the antiderivative of secant cubed. We had to do a little bit of integration by parts. And so let's see if we can remember this. So the basic idea was, well, you have secant and cubed, which I break up as secant and secant squared. The reason being that this right here, this is the derivative of tangent, and so that has sort of a nice antiderivative. So if we make this our dv, then we get that v equals tangent theta, which means that we'll set this part to be u, which means that du is secant theta times tangent theta, d theta. So I have a nice derivative. Okay, well, so what does that give me? So it gives me u times v, secant theta, tangent theta, then minus the integral of v du. So minus the integral of secant theta, tangent squared theta, d theta. Well, how do we integrate secant theta times tangent squared? The answer is we don't integrate secant theta times tangent squared. What we do is we use trigonometry. And in particular, we say, hey, let's think about ways I can handle this tangent squared. So in particular, in this case, tangent squared, I can replace that because I know that tangent squared happens to be secant squared minus 1. So this becomes the secant theta, tangent theta, minus, and if I multiply this in, I get the integral secant cubed theta, d theta, and minus plus integral secant theta, d theta. Now, the good news is, integral secant theta, that's on our list. That's something we should know. It's the log. It's that crazy log, right? Okay, so that's secant theta, tangent theta, plus log secant theta plus tangent theta, minus integral secant cubed theta d theta. Now the problem is, well, how do you integrate secant cubed theta d theta? Well, that's a great question. I know it's a great question because that's where we started. Wait, look. Minus. I can move it across. In fact, let's do that. So 2 integral secant cubed theta d theta is equal to secant theta tangent theta plus log secant theta plus tangent theta, And then I throw in a plus c. And the reason being that, well, these might not actually be exactly the same, but they're within a constant. So that's why you add a plus c. And now I divide by 2. So this is one of those, do integration by parts twice. You get in a loop, but then you break the loop by moving the term across and dividing through by a constant. So integral of secant cubed theta d theta is 1/2 secant theta tangent theta plus 1/2 log secant theta plus tangent theta plus c. And you might say, whoa, wait a second, 1/2 c. But constants are like sponges. They absorb other constants. And so we can just leave it in that way. So we're good. We're good to go. We're good to go. All right. Well, now we come back. We've just integrated secant cubed. So let's do it. So here we go. 1/2 secant theta tangent theta plus 1/2 log secant theta plus tangent theta. And then evaluate 0 to pi fourths. So we plug in pi fourths. So secant of pi fourths is square root of 2. Tangent of pi fourths is 1. Okay, so that's 1/2 times square root of 2. Plus 1/2 log square root of 2 plus 1. Okay, then plug in 0. Secant of 0 is 1. Tangent of 0 is 0, so the first term goes away. And then I get 1 plus 0, but log of that is 0, so that goes away. And so our final answer is 1/2 square root of 2 plus 1/2 log square root of 2 plus 1. Aha! Exactly what we would have suspected when we started this problem. Well, probably not. Probably not. But that's okay. We didn't have to. We have the tools of calculus to help us. And now you have those tools. And so you can do well on the test. But not just on the test, on anything you need where you're working with integration. So good luck, and see you on the other side.